Hello people, today we have probably the last lecture of gas dynamics, and it will be devoted to two questions. Turbulent boundary layers, which is the first one, and second one, some solutions of Navier-Stokes equations. Yeah. Discussion that we could devote a whole semester. But okay, it's very short because you probably already know what are Navier-Stokes equations and how to simulate various structures in incompressible and also incompressible aerodynamics. First, we take a look on turbulent boundary layer theory. And here I also would like to show you some videos that would be better explaining complexity of question. Turbulent boundary layers, you know, they happen after flow reaches some critical Reynolds number. And after this critical Reynolds number, laminar boundary layer transforms into a irregular structure. I will start the video where you can see propagation of turbulent boundary layer for different Reynolds number, different initial flow velocities. This video you can also find in the internet. This video is from, okay, let's see, University of Melbourne. It's test made experimental visualization of turbulent boundary layer. Is a comparison between two different flows with two different Reynolds number. One is 270, which is close to transition from laminar to turbulent regime, very small Reynolds number, where we can determine presence of single vortexes along the boundary layer. But you can see that we cannot estimate that profile of velocities close to parabolic as we saw in laminar flow. Here it's chaotic, here it's highly turbulent flow with different size vortex structures. And on the lower side, where Reynolds number is significantly higher, energy of turbulence is significantly higher, we can observe formation of smaller structures. You can see high volume vortexes and small size vortexes, and they form more chaotic structure with respect to smaller Reynolds number. Let's continue looking this video, evolving or moving in space, but also various structures of rotating fluid. We can see that it's not uniform, right? Somewhere we have a larger scale or larger size of boundary layer, in some other places where internal or external fluid enters in interaction with this flow structure. We see that there is also exchange happens with external fluid. So boundary layer by itself is not something which stays in itself. It quite intensively exchanges with external fluid, and this is why turbulent exchange or turbulent heat transfer is much more intensive than laminar heat transfer, because we have a massive exchange of mass and massive exchange of energy between external and internal volumes. Okay, there are credits which we are grateful to. Let's try to go. I will try to go next. Okay. Estimation of turbulent friction drag is presented on figure 1. This is an image from Van Driest, reference 47, which are also included in Anderson book. Formula 1 and 2 are giving to us estimation of thickness of boundary layer and estimation of skin friction drag on the surface of a boundary layer for laminar regime, for turbulent regime, for various values of Mach number. We see that since flow is compressible, we need to take into account not just Reynolds, but also Mach, the second dimensionless parameter. Reference temperature method. We did not touch this reference temperature method in laminar regime, but I think we can discuss here, and for laminar regime it's very similar. What is the reference temperature method? Is an approach to take into account compressibility effect, taking or using simple equations. For example, the idea for this method of calculation of friction drag is the following. We use formulas developed for incompressible flow, because incompressible flow is simpler from point of view of calculation and experimenting. So we provide experiments for incompressible flow. And using these formulas, which you can see on the screen, 3 and 4 for skin friction drag, we use, instead of viscosity and Reynolds number for compressible flow, we use some reference viscosity. Instead of real viscosity, we use reference viscosity. As we know, reference viscosity, or any type of viscosity, is a strict function of temperature. So this is why viscosity will be always associated with the temperature. Reference temperature method is using definition of reference temperature, which is related to exchange in turbulent or laminar boundary layer. And calculating this reference temperature, we are approximating to the real value of viscosity, and can use this value of reference viscosity in estimation of friction drag, estimation of thickness of boundary layer. How to calculate reference temperature? Here is the formula, which you can see here. First one is ratio of temperatures. T asterisk is reference temperature, and TE is temperature outside of boundary layer. TW is the temperature of the wall. ME is the Mach number outside of the boundary layer, and R is the function related to Prandtl number. Okay. Typically for turbulent flows, we use Prandtl number equal 1. So this R will also be equal 1. This reference temperature gives more approximate value of viscosity, which is after implemented inside Reynolds number, Re-X and Re-C, presented on following formulas. And with this new viscosity, we can estimate more accurately values of friction coefficient. Reference temperature method is approximate. Reference temperature method is based on empirical solutions and experiments. So it's not a consequence of application or solution of flow equations. It's an attempt for us to determine value of viscosity closer to real viscosity which we have in our system. Of course, this is very approximate approach, so reference temperature method can be used in preliminary design. Okay, in preliminary, on phase of preliminary design of flight vehicle or any structure working in incompressible and compressible fluid. So reference temperature method allows us to use incompressible equations, and with the correction in viscosity, we obtain compressible equations or compressible coefficients. Okay, same thing we have for a laminar flow. Unfortunately, I could not present you last time. I missed this slide. Reference temperature method for laminar flow is same, just friction coefficient for this flow will be different. Okay, this coefficient here. Okay, let me try. Today I do not have this opportunity I had last time, but okay. These two coefficients for compressor, for laminar and turbulent flow are different, okay? And same for these two coefficients. The approach is same. Reference temperature method was developed more than 80 years ago in 1940, but it's still very important and useful in preliminary calculations. Recently, approximately 17 years ago, there were publications about improved reference temperature method, which propose another function of reference temperature ratio. Okay, and this improved method you can find in the literature and also in Anderson book in chapter, I think, in the previous chapter, I think it was chapter 18, right? Or yeah, chapter 18. So it's actual and it's very helpful because with the use of this method, we can calculate friction without simulation on bodies for compressible and incompressible flow. Very useful. The modeling of turbulence is happening with various models, different models. There are models of different scale. There are so-called zero-dimensional equations, which do not involve any differential equations inside the model of turbulence. There are one equation model. There are like Spallard-Talmaras, for example. You probably saw it in ANSYS Fluent. There are two equation models, for example, K omega, K epsilon, which you also tried probably in ANSYS Fluent. There are three equation model, which is K, KL, omega, for example, implemented in ANSYS Fluent. And there are also other models, four equation model, etc. How many equations is calculated by number of differential equations in partial derivatives. So for high level of turbulence modeling, number of equations can be even bigger than number of real flow equations. You remember there is continuity, momentum, and energy. And for turbulence could be more and more and more equations. There is no best turbulence equation modeling, as I already told you probably in aerodynamics. When we are modeling turbulence, we are trying to find an approach which describes better one or another flow. For example, there are turbulence model like K omega SST, which describe pretty well flow around airfoils, right? But also there are K epsilon. K epsilon was also developed for airfoils, but also was developed for nozzles. For nozzles, we also can use Spallard-Talmaras model or other zero-dimensional models, for example. So each model is for specific applications. There is no best possible model. If you will think that, okay, more complex equation system describes better the turbulence, is not true. Because not just important the level of approximation of turbulence, how many equations you solve, but also how detailed is your picture, is your physical picture model. For example, how detailed you describe interaction between fluid and liquid. Where is this turbulence happen? Or it happens on the border of a wall, if the wall is straight, or it happens after flow separated from the wall. There are two very different cases. Many turbulence models require additional flow equations. For example, large edge simulation is or less models, they require special mesh. Okay, there are requirements for about number of elements. They also require to solution in only transient form. There is no solution in stationary form. In real life, we understand that turbulence or any flow process is always transient, right? As we saw on previous video, such a flow always changing. right? The boundary layer is exchanging energy, mass, momentum with external flow with wall. So it cannot be presented as stationary process. It's always something changes in this flow. And numerically also some models require only transient approach. So question of choice of turbulence model is much more advanced than just study of aerodynamics or study of gas dynamics. There are tens or hundreds of books written about choice of turbulence model or modeling of turbulence or specific details and specific aspects of modeling of this exchange of this process, right? Depending on what we must study, we choose an appropriate turbulence model. I hope you understand that it's quite critical to understand first for what you would like to use this model, and then you choose an appropriate model, and if you can use this model. In gas dynamics, Anderson proposes to us just one model, Baldwin-Lomax model, developed a very long time ago. It's one of the first models attempting to study turbulence or exchange. And this model is zero-dimensional. It does not have any differential equation in partial derivatives. Actually, what we see here in equation 5 is just implementation of model in the momentum equation, but the model by itself presented lower equation 5, below equation 5, does not contain any partial derivative. How the Baldwin-Lomax model is working? The idea is the following, that we will try to present presence of turbulence or this high energy exchange between boundary layer and external flow as an increase of viscosity. With increase of viscosity, local viscosity, we will model exchange of momentum and exchange of energy. As you might see here inside equation 5, we have sum of mu, which is dynamic viscosity or viscosity coefficient, plus mu T, which is a turbulent viscosity calculated by Baldwin-Lomax model. Okay, this sum here. Okay, this sum here. Mu is called molecular viscosity, is a viscosity of gas which always is present. Is this value is very small. I think it's around 1.8 10 power minus 5. Our usual viscosity, which we use to calculate the Reynolds number. Okay, and the mu T is turbulent viscosity calculated by model presented on this slide. Turbulent viscosity, as you may see on equation on the left, first equation on the left, is divided in two layers. So there it is a function which has two parts. Before crossover, before some specific point inside the boundary layer, and after. From 0 to crossover, we have inner layer, mu T inner, okay, and for from some coordinate to external point of boundary layer, we have mu T outer, outside of this inner layer. Inside the inner layer, turbulent viscosity is presented in this equation here. Is proportional to density, characteristic length, and angular velocity of fluid. Where here we have characteristic length defined by this equation. Here all parameters are given. Here you can see also y plus is present. So y plus is an important parameter because it enters inside the calculation of turbulent boundary layer. This is why we are always interested to have y plus in a certain range. Otherwise, estimation of turbulent viscosity would be very wrong, and boundary layer would be very thick. Probably you already saw for people who simulated airfoil with quite high value of y plus, you probably had also very thick boundary layer. This is why viscosity because viscosity was wrong. Let's say y plus is calculated by known properties of fluid density. Okay, I think it's shear stress and viscosity multiplied by y is coordinate. It's a coordinate. So y and y plus are connected linearly. Y coordinate and y plus function, y plus value. On the wall, you can say, okay, on the wall we have y plus y0, but not exactly, because our first cell, center of first cell is not exactly at the 0 coordinate. It's displaced from the wall on 1/2 of cell. So it's delta y divided by 2, the smallest value here. We can see that y plus on the wall is smallest possible, right? Because y plus and the coordinate is smallest possible. These parameters here, rho, w, tau w, and mu w are also functions. For compressible flow, we know that density changes from one point on the wall to another, shear stress proportional to velocity gradient, and viscosity on the wall also must be defined. It could be defined as constant, but also could be defined as function of quality of surface. And angular velocity, this function I hope you remember from aerodynamics. Angular velocity is calculated as the difference between derivative of u velocity by y direction minus v velocity by x direction. A classical definition of angular velocity. So this is for inner layer. You can see that according to this function here, since characteristic length is proportional to y coordinate, for inner layer, this function would be parabolic. Okay, I will try, but it's not absolutely not convenient to write in tool which I'm using here. Sorry. It's not okay. And for the outer layer of turbulence, of viscosity, we have another function. In this function, there are many parameters, where each parameter is calculated by its function. It is just algebraic manipulation of flow parameters. Sorry. With known constants, and okay, K here is conductivity coefficient, and KT is turbulent conductivity coefficient, PRT, Prandtl, turbulent Prandtl value. Here of Fy, we have to find maximum value, and only this maximum value we use in a definition of turbulent viscosity on the outer layer. So on the outer layer, viscosity is constant until flow reaches. Okay, I will try. Sorry, there is some problem with my mouse and it doesn't make straight points. So today is not nice to draw. I will try again. Okay, okay, constant value. In the inner part, viscosity grows parabolically, and in the outer part of boundary layer, viscosity is constant, since mu outer is constant. And then when we reach edge of boundary layer, viscosity becomes equal 0. So it drops to 0. So this is graphics of viscosity with respect to y coordinate. Here in this model, there are no, as I told you already, there are no differential equations. We just must analyze already existing functions. For example, even here in calculation of angular velocity, we are not solving anything. We just calculate derivative of known function. And by this procedure, we define in each particular point in x and y coordinate turbulent part of viscosity, and submit inside equation 5, and also we use it in energy inside energy equation because it consists also of viscous part. And then solve. With this solution, we obtain flow with the boundary layer inside. As before, to solve this problem, we must set boundary conditions, as I told you, for laminar or for general discussion, which we had on previous lecture. We must set zero velocity on the wall, right? Known temperature on the wall or known heat flux on the wall. And with these boundary conditions, we obtain all the flow picture. If you will try to implement Baldwin-Lomax model, I think it's not difficult. You can do it even in MATLAB. But for this, you must also solve together flow equations. This parameter as turbulent viscosity and turbulent heat conductivity coefficient, they are not thermodynamic parameters. They are not considered as thermodynamic parameters of the flow. They are received after solution of flow equations. So they are results of calculations, but they are not independent parameters which we set. They are included in the model and they are calculated inside the model, but they cannot be defined from outside, like temperature, pressure, or density. So pay attention that viscosity and heat conductivity for turbulence are not included in the list of thermodynamic parameters. Then application of Baldwin-Lomax model. There are two main applications which are very, very important. First of all, it can be applied in subsonic flow around airfoils. Okay? And second, it can be applied in internal flows. It will be very useful in calculation of nozzles, diffusers, in incompressible, compressible, and even hypersonic flow calculation can use this Baldwin-Lomax turbulence model. The simplest turbulence model we can find is this one, the simplest one. One important observation for use of this model can calculate only attached boundary layers. It cannot calculate the attached boundary layers because inside these equations we can see y, definition of y. Y is, okay, where is my pointer? Here. This y is distance from the wall, okay, to any specific point. Is not just y coordinate. Is a distance from the wall. Wall is having zero coordinate, and y is normally directed from the wall. So this model will work only when there is a wall. When flow is separated from airfoil or flow is separated from the wall, we cannot determine distance to the wall, and this model will not work anymore. So outside of the body with separated boundary layer, flow will always be considered as inviscid. Very interesting, right? So we have boundary layer just separated from airfoil or from nozzle or from diffuser. It's immediately considered as inviscid. This is typical not just for Baldwin-Lomax model, but also for K epsilon and K omega models of turbulence. Okay, so all these models must have a reference. When they do not see wall, they stop working. No, they don't stop working. They are not included in the solution anymore. So only in viscid part of flow is solved, and viscous part of flow is not solved anymore. There are a lot of models, various, and one of the best visualizations or one of the most complex simulation of flows I found several years ago. I would like to show you this simulation on next video. Okay, just a moment, it will load. Wait, just a moment, I will check quality because we need a good quality. I hope it's okay. on your screens. Let's see, this is simulation of turbulent flow around the wing profile. So it's three-dimensional simulation, but only a piece will be visualized, because if you see a whole wing, it will be, turbulence will be very small with respect to size of the wing, and it will be almost invisible. So they show us to us whole airplane, and then they separate just a piece of the wing for visualization. Okay, the airplane. Probably you could see this video already on YouTube. It's one of the best, I think, in this area. Angle of attack will be 5 degrees with Reynolds 400,000, so it's definitely highly turbulent flow. And then they separate part of the wing. And use direct numerical simulation. DNS model, which is probably the most complex model of turbulence existing in ANSYS Fluent. This model requires extreme number of computational elements. We can say that hundreds of millions or billions of cells are needed to make this simulation of turbulence. So it must be quite powerful machine to provide this simulation. It cannot be done on a conventional notebook. Just visualization of mesh. I think it's more visualization of how cells are going, but not the number of cells, because quantity of cells here is really, really huge, and it's three-dimensional. So we can see here C-mesh, mesh similar to simulation which we did in aerodynamics. C-mesh quite and also quite important to say that this volume is relatively small with respect to what we had before, because there are special boundary conditions applied to these control volumes. They are not conditions which we set in simulation of our airfoils. So these special conditions allow us to approximate volume closer to the body, but they require, let's see, 35 million core hours. It's 35 million processors, let's say, and more or less 75 terabyte of data. So you can imagine how big is the computer for this simulation. And the results of simulation by itself, and this model requires transient formulation, so it's only transient flow can be solved. Here we can see formation of turbulence. There is a way to track transition from laminar to turbulent regime. You can see this transition here. And then formation of turbulence. Unfortunately, frame rate is not perfect, but I hope when you see this video on your computer on YouTube, you will see all the beauty of this simulation. It's really, really nice. It's one of the best things I've ever seen in numerical simulation. We can understand about complexity and about how nice is this type of work, how nice it can be this work when you can by your own hands create such a result. You can imagine if you program all from zero to reach these points, it's exciting and motivating for many people. I know people who work all their lives in numerical simulation, and they are very happy with this. When you see this world which you create by your own hands, is something that is worth to do. So you can see how complex is the turbulent structure of flow. Here visualization is done by constant surface of vorticity. I think it was constant vorticity surfaces. And vorticity, I would like to remember you, is some way of presentation of angular velocity, rotation of fluid. So you can see, I just stop in several moments for you to understand the complexity of this flow. From the lower surface, from the upper surface, you can see that flow is never uniform. Actually, what we simulated in aerodynamics with K omega or K epsilon model does not exist in real life. This is what exists in real life. This is what we could see on real airfoil. But with the K omega, K epsilon average models, we can track also important thing. We can track behavior of skin friction on the surface. But unfortunately, with K omega and K epsilon model, we cannot see these details. This is what we are missing in 2 or 3 equation models. We miss these details, but we can calculate impact of this flow on a surface, resulting in skin friction at each point. I hope one day we can do this simulation in gamma. Unfortunately, nowadays is not possible. I hope one day our computers will allow us to have such exciting, beautiful simulations. Okay, von Karman vortex structure, which is repeating periodically. Okay, this is the collaborators. These are collaborators of this project. It's a huge computational project, of course, not of one institution, but of many institutions. And the last, I would like to show you the simulation of compressible turbulent flow. Just a moment, I will adjust also quality. Okay, I hope now it's okay. And let's see, here we can see formation of turbulence after shock waves. With the transonic regime, we have separation of flow because of impact of shock waves on the top part of airfoil, and then highly turbulent flow behind. Reynolds number 500,000. 4 degrees angle of attack, some special shape airfoil. And this simulation was provided at the University of Southampton, as you might see. This video also can be found. It's from YouTube. It's very nice simulation. You can see how complex is the structure of flow. So there is no chance to calculate it precisely analytically or with a simple flow model. I think the only way to provide such simulation is an advanced flow calculation. Here flow is colored on the top by blue and on the bottom of airfoil by red color. Just to visualize vortex structure. Quite nice, right? Quite beautiful. This is one of few things we can see for a long time, like fire, like flowing water, formation of turbulence or simulation with high quality models. This can be seen forever. And many people also would like to contribute to this study. And this is, I think, important. So this is all what Anderson proposes about turbulence and turbulent or simulation of turbulence, turbulent boundary layer. More advanced methods, advanced models can be studied in the next course of, for example, master course or doctorate course. Usually this is the subject to study because advanced concepts and mathematics is involved there. There is no reason to present on undergraduation discipline. End of part 19, part which is relatively short. You see only 11 slides here, and I would like shortly to show you chapter 20, which is where you can see repeated many concepts from previous chapters about some solutions of Navier-Stokes equations. Just a moment, let me open this presentation. Okay. I cannot see if there is a question. Please let me know. No, probably there is no question yet. Please type if you have some question in chat or say by voice. Not always I can visualize our chat because I'm working on another computer today. So no questions for now. We talk about some examples of Navier-Stokes equations. Very briefly, because I would like to finish today all this discussion. Generally, Navier-Stokes equations in form which we saw and you saw even before aerodynamics, right? Of equations of continuity, three equations of momentum and energy. All of them are written in transient form, and they are written in three-dimensional form. So these equations we use to solve a lot of complex problems. Also, this equation has source of energy, which is typically produced by external heating or a chemical process or electromagnetic heating or others. Different sizes, different sources of external energy. Viscosity included here, so we calculate all only by these equations. To complete these equations, do not forget to use equation of state and equation of internal energy or enthalpy definition, because otherwise number of unknown will be bigger than number of equations. So at least two more additional equations. And please do not forget that to calculate shear stresses, all included here, there are a lot of shear stresses. We must use an external turbulence model, one of many which we mentioned today, right? Starting from simplest Baldwin-Lomax, 0-dimensional up to 5-equation model, or even more DNS model, even more expensive model. Please do not use DNS model if you do not have computer with some few thousand of processors. But other models are okay. Some examples which Anderson gives to us. These examples are classical. I include same which Anderson shows is just to mention, right? The one of classical task is this one, rearward facing step, very simple from a geometrical point of view, where we have flow starting on the left side and then going in direction from left to right, and then it passes by a step. From computational point of view, it's simple. When you use Navier-Stokes equations, it becomes quite difficult, right? Solution, and this experiment also can be provided easily. So this task serves for validation of solution of Navier-Stokes equation. If you solve Navier-Stokes equation written by yourself, solver, you can compare with this task, and you can see flow picture, compare with experiment, and see if solution is correct or not. Not just in integral values, but values by many points along the wall or inside the flow. There are several classical tasks also existing for Navier-Stokes equations. They are tasks of flow around sphere, flow around cylinder, flow around airfoil. It's more complex. Flow inside the nozzle. This like here, incident expansion, also incident compression, where it's opposite geometry, and for incompressible and compressible flows, for subsonic and supersonic flows, these classical patterns of flow solutions, they exist, and they allow us to validate Navier-Stokes equations. So this is the main purpose. We must understand if our solver is actually solving as it should, or it has problems. Probably you understand that to solve Navier-Stokes equations numerically is not trivial task. So we must pass by many different. Oh, you should tell me that you cannot see my screen, because I'm showing and it's not appearing on your screen. Please let me know if you still see chapter 19. Hello, Mauricio?
Now it's figure 20.2.
Okay, no, because I disable and enable again because there was some problem of visualization. I see on another computer it was still chapter 19. Sorry, guys. So this was, I was showing very few things, not nothing of important, right? I showed equations of Navier-Stokes with the known parameters and examples of solution step, incident step. That is a classical task, solution to validate by our own code, and some examples of solutions, simulation around airfoil for different types of flows, for laminar and for turbulent flow, and three-dimensional flow, which under some sites is extremely important, like this X24C shear stress distribution, or distribution of shear stress lines on the surface of the flight vehicle. Okay, quite nice three-dimensional simulation. Another classical solution for viscous flow and for Navier-Stokes equation is this shock boundary layer interaction. It can be performed in various forms. It can be performed in this simple form with the flat plate and reflected oblique shock waves. It also can be performed in interaction of normal shock wave and boundary layer, or interaction of shock wave and some angle of attack or some inclination of the body. So there is an angle on which we have formation from which we have formation of a shock wave, which interacts with boundary layer in such configuration. All of these examples, I think it's worth to discuss with people who would like to continue study of gas dynamics in further courses, or to make some scientific research. Is not for all, I understand. This classical task of interaction of shockwave and the boundary layer, I think we already had this discussion when we talked about boundary layer and shockwave some previous chapter of gas dynamics. Some simulations. This simulation I like a lot because this is my simulation from my work. And you can see incident shock wave, reflected shock wave, and one important aspect which I explained you on one of previous lectures is that zero pressure gradient on the surface of a wall. So since we have a boundary layer, all pressure lines are perpendicular to surface. So approximately perpendicular, because this visualization from triangular mesh, so it was made an approximation of results. Another examples which Anderson shows and significance of these simulations of Navier-Stokes equation. For example, we can see large-scale simulation of an airfoil with protuberance. What is protuberance? Is some small defect on the surface of an airfoil. The small defect is or could be ice, or could be some dust, or could be something that is changing geometry of the airfoil, and with the change of geometry, all other aerodynamic properties also suffer. So this small defect is not visible from far field. It's not visible on the closer view, but when we zoom more, okay, this is this protuberance here. This is the simulating change of shape. It's very, very small with respect to size of an airfoil. Since we know that all on airfoil influence on all, this creates huge problems everywhere around airfoil, even being of a very small size. So unfortunately, Anderson shows not in a good quality these vector lines, but we can see that there is a vortex behind protuberance here, vortex which is destroying the flow, and flow is going around not just protuberance but also around the vortex by itself. So amount of recirculated flow is big, and it increases with along the length, along the airfoil. We see that vortexes are separated periodically from the lower side of the airfoil, and this happens because of presence of very, very small defect on this shape of the airfoil, and this can be seen only with simulating viscous flow around this aerodynamic body. Okay, some results of application of different models on NACA airfoil. For different models, we receive different shear stresses. You can see that for K epsilon, RNG K epsilon, Reynolds stress model boundary layer solution is the application of boundary layer equations. We obtain different values of friction coefficient. Here there is one mistake. It should be 10 minus 3, right? No, multiplied by 10 power 3, so we receive this. But when we see on the graphics, we see that it's 10 minus 3, more or less. Difference between different turbulence model can be big or not significant, depending on application. As I already told you, some turbulence models are better from the others on very specific tasks. And we must remember also, even for Baldwin-Lomax, for example, that the model has several coefficients inside. Each turbulence model is adjustable. It can be adjusted according to reference simulations or according to reference experiments. Okay, here Anderson shows that can be significant difference between shear stresses along the surface for different turbulence models. Okay, people, I think that's all which I had to tell you about simulation of viscous flows and generally about gas dynamics. By this, we can finish our lectures on aerodynamics and gas dynamics. Is the final part. I would like to thank you for being so long at my classes, and I hope you liked, and I hope you will remember at least something after these classes. And now it's time for you to ask questions. Our next lectures will be in format of your questions. If you have questions, please send in the group and we will discuss. If you have questions on theory, if you have questions on some calculation of examples, or questions about practical works, right? We will organize our meetings for people who are interested to hear answers on these questions. It's not obligatory for all to participate in our future meetings. I think that since today we finish classes and lectures, next meetings will be just for people who need a solution, who will search for solutions, right? So that's it. And please let me know if you have questions today. I see no questions. So I thank you very much for participation in aerodynamics and gas dynamics. And I wish you good luck in sending work 1 and 2. And I wish you also good evaluation at the end of semester. And we keep talking until this time. Anytime you need, please let me know. Have a nice afternoon. Thank you.